Good afternoon. Welcome to course Thermodynamics of Materials. Today we are into lectures 163 and 164. We are discussing the Gibbs Phase Rule and we are taking up 12 examples. 12 examples. See here, 12 examples that will be taken up for the purpose of illustration. So the first example is M plus half O2 goes to MO solid. We discussed this last class. Just quickly run through this, okay, what we discussed. So how will you make a phase rule analysis? We say make a phase rule analysis of this equilibrium. This is a reaction equilibrium. So of the system, this system is actually is a reaction system. So I have labeled it as 1, equation number 1. So this is maybe addition from the last class. So start. F is C minus P plus 2. See, this is the standard procedure of making a phase rule analysis of a system. What is this? F is C minus P plus 2. Then C is find C and find P. And C, you see, how many? There are two ways of finding C: through the number of species, from the viewpoint of species, and from the viewpoint of elements, number of elements. So both you will see they coincide. So so number of species minus number of reaction equilibrium. So number of species is what here? 1, 2, 3. MO, O2. 3 species minus the reaction, only one reaction. 3 minus 1 is 2 is the number of components. From the viewpoint of number of elements, what is this? Number of elements minus number of stoichiometric relation, none. This actually, so only number of elements is 2. Typically it will be number of elements, most cases. So 2. So 2 and 2, so they coincide. So it is okay, fine. And see here, when it is number of elements, M and O, these two, okay. So C is 2. From this we get P, number of phases is 3. M, 2 solids, M and MO, and another is gas. Third is the gas. So 3, 2 minus 3 plus 2 is 1. 1 degrees of freedom means if we fix, by fixing, you have to demonstrate how by fixing F number of variables, this state of the system can be completely defined at equilibrium. So by fixing one variable, pressure you don't have to, and you cannot, in fact. One, it may pressure, but in that case it will not be temperature. Just one. So temperature, say, for example, temperature 800 Kelvin, just for example, 800 Kelvin. So see, you will say automatically pressure will be found. This system is such that fixing temperature will be able to define the system completely, means in terms of temperature, pressure and composition of each phase. So start the temperature, say for example 800 Kelvin. So fixing, so demonstration. So demonstrate. We have to demonstrate how by fixing F number of variables the system is defined. Fixing T fixes KT, equilibrium constant. Equilibrium constant is a sole function of temperature. So equilibrium constant KT is K800 here. So what is this expression for K? Activity of product by activity of reactants, activity of MO and activity of M are ones, and activity of gases are partial pressure. So this gives rise to 1 by PO2 equilibrium. So from this you will get, since KT is known, tick mark means this tick mark means known. It is known. Fixing T means I know T 800 Kelvin. So find out delta G0, from which you get through minus R T ln K, that's K 800 or KT in general. So 1 by PO2. So you get PO2 is found. PO2, since it is only the single species, so PO2 exerts, PO2 is the total pressure as well. PO2 pressure, oxygen partial pressure is also the total pressure. See the system here, metal oxide, oxygen in equilibrium. See the temperature, pressure. Okay, see we have independently fixed only one which is allowed, one only, and then pressure will be automatically fixed. How it is coming? P is PO2, and so this is automatically fixed. So only one gas species. So finally composition of each phase is what? Metal pure. Pure means mole fraction 1. Metal oxide likewise pure means mole fraction of metal oxide is 1. And gas phase is what? Gas phase is PO2. PO2 you have already partial pressure wise you know this. If you want to get mole fraction wise, since only single species, one species only, so the sole species is oxygen. So XO2 mole fraction of oxygen will be just 1. So PO2 by P means 1. They are same, they are equal. So by fixing, so this comment I made actually today, we start from here as it start from here from for today's class as it, and also this diagram also I will explain. This I drew last class, but I have redrawn this, and so additional discussion will be made, okay, on this diagram. So I will talk on this, but first finish this part. So by fixing, this was the purpose. By fixing, demonstrate how by fixing a number of variables. So by fixing one variable, f is 1, t here, the remaining variables are automatically fixed, and the system is fully defined or described, as you may call it, in terms of temperature, pressure and composition of each phase at equilibrium. So this is clear demonstration of the Gibbs phase rule. Okay, so fixing this, everything is, see, composition is known, temperature we have fixed ourselves at the very beginning, okay, independently, and pressure, total pressure is also found. So temperature, pressure and composition. Now there is some linkage of the degrees of freedom with the stability diagram. So see, we can actually interpret degrees of freedom from the stability diagram also. So, but how will draw this? This stability diagram is drawn, as I am telling you here. Okay. Remember, these figures, don't worry. This is for the next example. This figure, and this figure also for the, okay, third example. So these two figures, please ignore these two figures. Just concentrate here. This is figure 1B. This is 1A. This is 1B. What is this? This is stability diagram for the system metal oxygen. This is two component system metal oxygen. So metal oxygen, it is what? ln PO2 versus 1 by T plot. Sometimes we can also consider log PO2. ln PO2 and log PO2 is actually separated by factor of 2.303, so no problem. So it is up to you. ln PO2 versus 1 by T. So this actually emerges as a straight line, and I will explain you now how it is straight line. So please follow. So today's class actually starts here. So delta G0 is, let me check actually, delta G0 is, right here about stability diagram. Okay, this part is over. This part is over. Okay, so that's discussion is now on stability diagram. Delta G0 is A plus BT. Remember what is A? A is typically, it is two term expression for delta G0 as a function of temperature. Remember, don't forget all these things. It can be 3 terms, 4 terms, 5 terms, depending upon delta Cp. Now delta Cp for this reaction, if it is considered negligible, is 0, say then it actually reduces to 2 term expression for delta G0, which is A plus Bt, where A stands for delta H0, the standard enthalpy change, and B minus delta S0. Okay, so remember this. So this is actually, even this is what? Minus RT ln K. What is the K? Actually a moment ago it is done. K is what? 1 by PO2. K is 1 by PO2 is, so can I write it here? Shall I write it here, or let me write here? Is minus RT ln K is 1 by PO2. powered half 1 by PO2, right? This powered half 1 by PO2 power half. Okay, so this gives you what actually is nothing but you just did this half RT ln PO2. So PO2 versus T relations we are trying to get. So objective is to find the relation between ln PO2 and 1 by T. We are about to get it. Or what you write? ln PO2 is what? A by 2A over R times 1 by T. First term, A plus BT. Second term is what? 2BT, 2 is 2B, sorry, it is actually 2BT by RT. This T cancel. So what is you are getting? This is actually this A. This A is a constant actually, which is delta H0. Constant means independent of temperature because of that property of delta Cp is 0. So it is, call it A prime 1 by T plus call this B prime 2B by R. So what is this? So ln versus 1 by T. It is better I write here. So right here. So ln PO2 versus 1 by T. What relation it is? Remember, ln PO2 versus T is non-linear because it is 1 by T. Related here as 1 by T. Non-linear. But if you plot ln PO2 versus 1 by T, then it is linear relation. Versus 1 is a straight line. Is linear. The relation is linear. It is not let us is linear. And what means straight line? And what is the slope of the straight line? The slope is what? Slope being A prime, and A prime being which is A prime being A prime which is negative. Why negative? See, negative line. So I have drawn negative. Okay, which is negative because A prime includes. Oh, by the way, because A prime includes A, and A is delta H0. So A prime includes A, that is delta H0 is negative. Why it is negative? Delta H0 negative. You remember? Delta H0, this is an oxidation reaction. Delta H0 is negative. Oxidation reaction. Oxidation reactions are negative and dissociation reactions are delta H0 is positive. Enthalpy change is negative for oxidation reaction, so negative. So slope is negative. So I have drawn correctly. So this line, so start from this. So first we draw this ln PO2 versus 1 by T through this relationship and we draw this. Then what does it mean? This line, concentrate on the line. This is the diagram, main diagram, about which other discussions will be built up. So main line we have drawn equation 1. I have written equation 1, this one. So equation 1 is drawn. This gives the equilibrium of this reaction. And what it implies? Equilibrium coexistence of what? this, and this, M solid, MO solid and oxygen gas along this line, okay. So always actually they have these three phases, 1, 2, 3, three phases. We have got three phases. So three phases is three phases are actually coexisting along this line, means it is representing this equilibrium. So this line is okay. Then the question is, another thing is, you should note this. Now along this line, three phases, but above the line and below the line, some other story. Above the line, below the line. This will be required, or this will actually, this feature will come, okay, this point will come over and over, okay, in the subsequent diagrams. Always line and above and below. Always, or to the right or to the left, whatever you call it, same thing. So given this, that, so along this, so suppose one thing, first of all, see, degree of freedom is 1. So what it means? You have one, you suppose you fix T as T1, fixed arbitrarily 1 degrees of freedom. So along this line means, again I told, one dimensional thing, one dimensional geometry. So it is one dimensional, that means degree of freedom should be 1. So this is 1. But later on I warn you beforehand, when you see a line, it is not necessarily degree of freedom 1, because you should know under what constraint it is 1. Is there any constant on the top, that constant pressure, constant temperature? This you will see. For example, okay, you might see actually here this type of things, okay. So one dimension, so don't actually jump into conclusion that it is 1 degrees of freedom, since it is a curve or line. You will ask actually whether there was any condition imposed beforehand, before the drawing. That means this drawing accompanies some stipulation, some conditions, like say temperature under a constant temperature, means one freedom is already there and 1. So 2, then the answer will be 2. If 2 already fixed and a curve, for the curve will get 1 and 2 already, so 3, like this. But in this case, no constant, 3. This equation is there, I have plotted this, okay, for PO2 versus 1, okay. So you can draw this curve, okay. I will take actually in details the construction of stability diagram later, but today this will be enough. This will suffice to say that this is the equilibrium, okay. This represents the equilibrium, this equilibrium, okay, this reaction equilibrium, and okay, and which actually involves the coexistence of M solid, MO solid and oxygen gas, like this figure also. M solid, MO solid, oxygen gas at equilibrium. This is represented by this line. Now, so one thing, see degree of freedom 1 from the figure also. See as I said, this phase rule, Gibbs phase rule, as well as this stability diagram are actually a kind of involved, intertwined. You cannot actually see here you apply. From this you will apply degrees of freedom. How? Your degree of freedom is 1, so you fix temperature T1. So I have written here T1. So T1, see, to have these three phases together, see, you actually have to hit the line, hit this straight line. So this point means PO2, corresponding value of PO2 here on the y-axis is automatically fixed. See, temperature, follow, temperature you fixed arbitrarily, 1 degrees of freedom applied, and there is no more freedom left, expanded. So 1 go up, and then you see the PO2 value, partial pressure of oxygen, is automatically fixed here. It cannot be anything else, dependently fixed. PO2 is very important. PO2 by itself is important, as well as PO2 is equal to total pressure. Total pressure of the system P is also the same value. So this fixed dependently. This is interesting. For example, if you say why it is independent, see, you can choose T1, you can choose here another temperature, free. But this one, once you fix this, this is automatically fixed. Subject to this value, this is fixed. Now at the same time you take up like this, okay? You fix the other way around. You don't you consider the PO2 as the degrees of freedom. Is the chosen degrees of freedom, chosen degree of freedom. So PO2 here. You walk from this side. For this PO2, hit this line and come down. This is the temperature. Here temperature cannot be changed. Temperature is fixed here. Temperature will be dependently fixed. Okay. So either way. So if fix this, this is fixed. Fixed T1, PO2 fixed. If fixed PO2, T1 is fixed. Okay. So it is very satisfying. Now another question is, another problem is this. This is about actually the coexistence of all these phases, means about this line. So for this okay, line, you have degrees of freedom 1. Okay. Now you see, if you actually go above the line and below the line, above the line, who is stable? See, metal oxide, you see, metal oxide here together coexist. But above the line, only metal oxide, MO, M eliminated. And below the line opposite, who is present? M solid, MO solid eliminated, oxygen. Why this happens? Follow this. For given temperature, if you increase so there is the equilibrium value of PO2, see here. Now, what you are doing essentially, this I will explain you, okay? Explain to you actually. You are actually violating the phase rule. You are exercising more freedom than you are entitled to by the phase rule. Phase rule says you are allowed 1 degree of freedom. But when you go up above the line, means 1 here, this is fixed, but you are choosing PO2, not this value. So here, freely. This is free and PO2 also free. Then you land into this single phase, means solid wise, MO solid stability region. This is the stability domain of MO solid. And of course, oxygen plus oxygen I have written in bracket, because this is implied. Oxygen must be there because the left hand side, the y-axis, refer to the y-axis, it contains PO2. So oxygen gas inescapable. So MO solid plus oxygen. Also from the concept of thermodynamics, what? If we increase the oxygen pressure, suppose this is in equilibrium, increase oxygen pressure, this will move to the right hand side. And as it is, and if you maintain this pressure more than equilibrium, it will continue oxidizing all until the whole of main solid is oxidized or removed. So what will be the final state is MO solid and oxygen gas. That I have it. The opposite will happen when you come below the line. When you consider below the line means what? PO2 is less than this equilibrium value. Here also again same thing, you are exercising. This is the kind of, this is also another way of exercising extra degree of freedom. You are entitled to this pressure of PO2, but you are changing it. Means you are applying freedom on the first PO2 also. In addition to temperature already there, and then you are actually working this one, changing temperature arbitrarily fixed, PO2 fixed. Then 2 degrees of freedom, that will actually give rise to so what will happen? The single phase. Here metal solid will be present along with, of course, the oxygen that is showing on the y-axis here, or on the y-axis. Okay, so refer to this. So which solid phase is present? Suppose this is the main question, metal solid. And which solid phase is present above the line? MO solid. Below the line, M solid. And along the line, both solid wise. And gas phase is always present. Okay. So here also you see, so when you increase the oxygen pressure, it moves this direction. If you decrease the oxygen pressure, decrease from the value of equilibrium PO2. So when equilibrium, this is in equilibrium position, and then you are exceeding the equilibrium value, the reaction move in this direction, and you sustain it. Then move, metal is eliminated. As I have shown, metal oxide will be retained. And when you actually decrease the oxygen pressure below the equilibrium value, then decrease this means MO will move in this direction. The reaction will move in this direction, and MO will be dissociated. Okay, until MO will be eliminated, and what will remain? M solid and oxygen. M solid and oxygen. So this part actually, let us have some writings here. Okay, there is negative oxidation reactions. So all these are still, all points are discussed, but it is better we actually write few lines here. So this is what occurs. So yes. So I'm just writing this. If F is 2, okay, this point. If F is 2, 1. If F is, it cannot be 2. If degrees of freedom, or freedom is actually, if is made 2, if F is made 2, means you are exercising two freedoms. So namely, temperature, your temperature 1, another is temperature, and P, okay, PT, say PO2, say PO2. Then you see, mathematically, see, so interesting, the what you observe here. What you observe here, you get here mathematically also. So F is made 2, then F is C minus P plus 2. So F is made 2 means increased from 1. When it increases, what I said, C unchanged, C cannot be changed. P decreases. So if F is increased to 2, so P will decrease from how many phases was there? 3 phases. It will decrease from 3 to 2. So you can check this. Okay, F is made to 2. When it is 2, C unchanged, C is 2 minus P, say unknown, say unknown. This leads to what? P is 1. I'm sorry, P is 2. What is this? 2 phases. What are they? Okay. Okay. Is okay. So it is P is 2. 2 is what? So two possibilities of applying 2 degrees of freedom, either above this line or below this line. So P is 2 is what? You write this P is 2. Is okay. MO, what is this? MO solid. I'm writing this. MO solid plus oxygen gas. Two phases. Or when you actually apply in this direction, the extra freedom you are apply in this direction, that is above the equilibrium PO2. Yeah, then this happens. Okay, or below, or what is possibility? Or M solid plus O2 gas. 2 phases. In either cases you are violating. Okay, either it is actually increasing the PO2, okay, increasing it beyond this equilibrium value. Okay, so increasing this PO2 from the equilibrium value, and or decreasing the PO2 from the equilibrium value. So in either case, see, it is okay, everything looks okay. Then
29 minutes करना. ठीक है. Okay.
Don't touch. It's okay. So in either this MO plus is okay.
This one is okay, but open it. the topmost line, that lecture 63.
That was initially okay. That happens. Okay. Anyway,
Then
this is okay. Focus is okay.
Yes, focus is okay. Everything is okay.
So two phases. These two phases. Okay. Possibilities is what? MO solid. If it is above this, okay, this line, this is, as I have already explained, MO solid plus oxygen or M solid plus oxygen, depending upon whether it is can't be it has been greater than PO2 equilibrium, is a three-phase equilibrium. PO2 equilibrium value here, this value more than this or less than this, in the form of an extra degree of freedom. So, and you have to, then a solid phase will be sacrificed. So in this case, what is sacrificed? Metal solid has been sacrificed, and here metal oxide has been sacrificed. So this is actually in nutshell about this. So this is okay, very good. Now I will take up some corollaries for this. So so corollaries. Okay, let us start. Corollary. One corollary. This is better I write corollary 1. This I have already discussed. Okay, I am saying what is the first corollary. It is not necessarily see 1 degree of freedom, how you are exercising, how you are applying this, you are fixing temperature. This is the freedom. I have written here temperature. In this diagram also this temperature. This is how useful this diagram to understand the application of the Gibbs phase rule or manifestation of the Gibbs phase rule. So that's how important it is, this diagram also. Fix here T. So you are fixed and this is automatically fixed. So what I said, there is no compulsion that it should be T. This you should note very importantly. 1 degree, number of degrees of freedom is very important. What is that value? In this case, 1. Who is that variable? Flexible. Your choice. What? Yes, temperature. It can be PO2 or say P. P is PO2 here. Interchangeable. P. Possible. So P here. So start from this side. P fixed. Then automatically temperature will be this. If I change the PO2 here, this will be temperature. So very good. So this I am going to write this one. Corollary 1, this part. And additional remarks. Okay. So note. We could fix P instead of T. We fix P. Let us write this side. We could fix P, which is also equals to PO2. In a simple case, this is a very simple case. When there are two species, gas species are present, of course, P total pressure will be shared by the two gas species. Here, single species, sole species is PO2. Okay, so PO2 and the total pressure are synonymous. So P is PO2. Yes, instead of T, if you could fix P is PO2 instead of T. As the available degree of freedom, degree of freedom okay. No, we could degree of freedom. Okay. In that case, actually, it can be shown also mathematically. You can show in that case, see, mathematically show that fixing PO2 or P, you are finding out T. So with this T, you see relation. Fix from PO2, known PO2, So when you know T, see follow. T is very convenient, remember. Most convenient. Because it is easy to vary temperature also with the help of a temperature controller. So anyway, pressure also you can change, okay, with the help of actually pressure gauge. So anyway, so temperature very easy also for mathematical treatment. T means T fixes KT fixed, from which PO2 fixed and total pressure also. So converse, PO2 is fixed, how to get T? This side to that side, that's 800 or whatever. So I am showing you quickly. This is thermodynamic exercise. Okay. In that case, okay, so in that case, just quickly one case. So you should be very much confident, or you should be very much actually clear about your concept is this. In this case, is delta G is A plus BT. A and B are known. From data book. A plus BT. Okay. Anyway, so yes. Okay. This is okay. This is A plus BT is continue here. A plus BT is what? Is minus RT ln KT of 1. KT of 1. Okay? Is what? Minus RT ln 1 by PO2 power half. See, K is 1 by PO2 power half. Is what it is also equals to half RT ln PO2. So now you see you are almost close. So it is better actually I should not. I want to remove this. Application. This all lines are removed. 12 examples will be given. I have already said. So don't worry. Don't worry. So start from here. So or what you are getting? See. So see, delta GT is I have written A plus BT. So it is better you write or A plus BT is what you are getting, half RT ln PO2. What is the PO2 that you have fixed actually? ln PO2 is what? PO2 incidentally is your P, same as P. See, you have consider P instead of T. You have fixed P. So P is known. So P known, R known, A known, delta is 0 from data book. B known. This leads to what? T can be found. T is known. This list. T can be found. So fixing pressure, so mathematical also. Fixing PO2, when you fixing PO2 or P, synonymous. Fixing P, I reach T. First case, here, fixing T, I reach P. Fixing T, the other variables are all other remaining variables. For example, pressure, very important. Okay. Pressure is known. Here converse. Pressure is known, pressure is fixed, P is known, P is for P I have fixed certain value. 0.1, 0.2, 1, 2, 3, etc., whatever. So knowing this, I can find out that corresponding temperature, this which is dependently fixed. So since PT known and otherwise composition also remaining the same thing. Okay, so pure solids and gas phase is the okay. This situation. Metal is pure metal oxide. So that you can write also. So how? Hence you can write hence all. So by fixing one variable, 1 degree of freedom in the form of pressure, all other the system can be fully defined in terms of pressure, temperature, and composition of all phases. Write that. Hence, you can write this. Hence, the system will be defined, completely defined as before. Defined as before. As before means as here. Completely defined here. Composition wise here and temperature pressure already. So temperature, pressure, and composition. So this is okay. But extra note. So I am removing this. I cannot remove this. But I have to remove also. No way. I have to remove note. Let us see how much. Note, this important. This I have already said. Finding, this is very important thing about the Gibbs Phase Rule. Important idea. Important point about the Gibbs Phase Rule. I have said already, okay, one very important that it is applied, it is derived under the consideration that the mass of each phase is given. For a given mass of each phase or moles of each phase. This is actually given. It can be 1 mole. In that case, actually the individual moles will be mole fraction. But this one point you remember. What else I said you, okay, is about the definition of components and degrees and concept of and definitions of alternative definition of degrees of freedom. All these things. Also, actually, I told you another thing. I told you what? Yes, this one. This I which I am writing now. That is what? What is the value of the degrees of freedom? Important, very important. Not which one that. Suppose F is 1, then which one that you are not sure, or rather you are free to choose, and that is flexible. This is I am writing. Finding the value of the degrees of freedom is better. I remove this. No way. Remove this. Okay. These are already enough discussion. Degrees of freedom. What is the symbol F? Finding the value of the degrees of freedom is of prime importance. Is of prime importance in the study of the phase rule. The study of the phase rule. Okay. Which variables the F represents F is secondary, and is secondary and a matter of choice. And a matter of choice. The F number of variables can be chosen from any of temperature, pressure, and composition. Composition expressed in terms of mole fraction, okay? In terms of mole fraction, or sometimes partial pressure. Okay, partial pressure is mole fraction when the total pressure is 1. Okay, so partial pressure, okay, you can also consider this in the mole fraction or partial pressures. For mole fraction, if you want to get partial pressure, mole fraction times total pressure. If it is 1, then they are exactly same. If it is not, then it put the value of total pressure, then get the partial pressure. So they are actually closely related, or partial pressures. And these are about gaseous species, okay, or partial pressures for gases, okay, or partial pressures in terms of mole fraction or partial pressure, either alone or in combination, depending upon the value of X. Have you understood this? So this actually, as already I have discussed, so no point. So how many degrees of freedom? Essential question, most important. Primary, how many degrees of freedom? Answer this. Then which are they? Not sure. This is a matter of choice. Say 1 degree of freedom, which are they? Say it can be temperature, it can be pressure, it can be partial pressure, like this. Or this is okay. If F is 2, it can be what? Temperature, pressure, or it can be temperature and composition, mole fraction, or partial pressure. 2, any 2. Pressure and if there are number of components, pressure and partial pressure will do also, no problem. 2 species are there, so we'll actually have a number of examples, so we'll understand that. But can you tell me what is either alone? It can be chosen from temperature, pressure, and composition. Either alone when either alone or in combination. As I said, alone when degree of freedom is 1, alone. Single. Temperature alone or pressure alone, because degree of freedom is 1, and more than 1 in combination, temperature, pressure, or temperature mole fraction of a species A, oxygen, like this. So this you know this. Now let us take up the next corollary. Okay. So this is okay. You know, hello. Corollary 2. So this is just remove all these things. Okay. All these things, actually these are not needed anymore. These discussions are over. Only these two figures don't consider. These two I'll make a barrier here, okay, a fencing here, so that or actually this I'll do this. I make a fencing, then I'll do this. So remove all these things. Remove this, remove this. Remove this, okay, corollary 2 and corollary 3. 3 corollaries will be discussed. First corollary is over. It's okay. It's very good. Very good. This one, let us have. This is. Let me correct. This is that. It should be an arrow here. I hope I have actually not damaged anything. So this is your fencing. This will be used subsequently when we take up second problem. This is about second problem, this is about third problem. 12 problems will be discussed. This is the first problem running. Okay, corollary to this is one. Another thing is what I wanted to, this corollary 2. Although this is about first problem, corollary from the first problem, corollary second. What is this? Corollary 2, yes. Suppose I tell you what I am going to consider. This figure, actually, I'm drawing that figure for you. This will help you. I've removed that though, but it is good idea that this is again as if redraw what you did before. This is the temperature, this is the pressure, and what are the phases? The oxygen gas, the metal solid, MO, solid, okay, and oxygen gas, of course there, but we introduce a complication. What is the complication? Metal solid may have some vapor, will exert some vapor pressure. We may consider that. All condensed phases have equilibrium vapor pressure. We call saturated vapor pressure. So here also it exerts vapor pressure. So that will be in the gas phase. So oxygen gas, oxygen and oxygen gas, metal gas means vapor. Vapor is the gas, metal vapor. Okay. So this, if we include this, how this will affect the degrees of freedom, and how will you demonstrate? Finally, you have to demonstrate. What you have to demonstrate? By fixing a number of variables, the system, the system will be fully defined in terms of temperature, pressure, and composition of each phase. So do this, okay? So I have added this. So corollary 2 is what? So let us write this. Suppose we intend to, this is one time, for once I am showing you, if you include this, you might argue actually. So metal vapor will be present also. Further matter, it will be more complicated, metal oxide vapor. But I am showing you one complication, metal vapor you will understand. Then you see actually it is consistent with the Gibbs phase rule. Number of components, phase will change in such a way that it will change such a way that that system you can like explain. You can define the systematic equilibrium, the state of the systematic equilibrium in terms of temperature, pressure, and composition. Suppose we intend to include M vapor. What is this? In the given system. In the given system. It stands to reason that M solid will exert equilibrium, which is called saturated. This equilibrium means saturated. Equilibrium or saturated vapor pressure in the system which is often negligibly small value. Particularly for solid, very small, unless it is actually very volatile solid, okay, which is often negligibly small. So he ignores sometimes, okay, but anyway, once we include this, let us see how we will explain. Yeah. how we defend the phase rule, Gibbs phase rule, okay, negligibly small value. But in principle, make a phase rule analysis. Let's make a phase rule analysis including the metal vapor, that is in the gas phase, metal vapor. Okay, figure 1C, figure 1C. 1C, figure 1C. Okay, this is your figure 1C. This is under equilibrium. Always under equilibrium, we are applying the phase rule. Figure 1C. Okay, very good. Nothing else. Okay, very good. Oxygen, metal vapor. Very good. So start of the same way. Demonstration of the Gibbs phase rule. Finding the F and show how. Okay, by fixing F variables, the system is defined. Start. Right, phase rule. F is okay. F is C minus P plus 2. Okay. F is C minus P plus 2. Okay. C is what? Number of species minus number of independent reaction equilibrium What is this here? Number of species. How many species? You see clearly. See what are the species? 1, 2, 3, 4. 4 species. Metal solid, metal oxide solid, oxygen gas, and metal vapor. 4 species minus how many equilibrium? Previously, reaction 1 that is already there. Okay, so that is one. Okay, so it is better I write here number of reactions. Okay, it is better I write this side. Okay, reaction equilibrium. Because this is not one reaction equilibrium. What are these? One is metal solid. I am sorry that I knew this metal solid plus oxygen half O2 gas is MO solid. This was, remember what is the level? 1. I have removed this, but this was already written and we are under that title. Okay, so what is this actually? Problem 1. For problem 1, this is already there, and then another is now included another one. What is that? Phase equilibrium. Okay, reaction equilibrium, phase equilibrium. This is all under the head of chemical equilibrium. So metal solid goes to metal vapor. This is second. So how many reaction equilibrium? 2. So what is the number of components? 2 from the viewpoint of species. Now see from the number of elements. I am not writing number of stoichiometric. There is no question of stoichiometric restriction, so I am not writing that. Minus number of stoichiometric restriction. So what are there? How many? Is 2. Again 2. Who are there? M, O. Has not changed. M and O. Okay, nothing changed. So C is 2. So these are in agreement. Okay. So we are happy. So I apply this. C is 2. How many? Right here P also. How many phases? Let's see again. See 2 solids and gas phase. 1 gas phase. Because 2 gas phase you don't consider. Gases are miscible in all proportions. Vapor is the gas. Gases are miscible in all proportions. So this is 1 gas phase. All gases constitute 1 phase. Gas phase. So 2 solids. So 3. Like before, 2 solids, right? M, MO, and gas phase, and a gas phase. These 3. So 3. Sorry. 2 minus 3 plus 2 is. If it looks good, okay, time, how much left?
1 hour 4 minutes. 1 hour left. Still 1 hour left. 56
Still 1 hour left. 6:20, 7:20. That's very good. Okay. And one thing I forgot to mention at the beginning, actually, that reminds me. Today is December 31st, 2025. So this is the last day of this year. So, okay. So I'll tell you Happy New Year, okay, after the conclusion of this class, okay. So anyway, move on. So 2 minus 3 plus 2 is what? What? 1. Again, choose anything you like. Say temperature. Temperature very convenient because it immediately gives the equilibrium constant. So fixing T, you can see 1 temperature. So let us fix. So fixing T. T say any value 500, 600, 700, 1000, 1200 Kelvin. Fixing to fixes equilibrium constant. Say 1 give. So KT 1 is what it is? Well, you already know 1 by PO2 is all implied equilibrium. Equilibrium. This leads to what? This is known. Fixed means this is known. So PO2 equilibrium is known. PO2 equilibrium is implied equilibrium. PO2 is known. Again, fixing T fixes likewise. This is also delta T0 is there, and temperature dependent equilibrium constant is there. So that is function of temperature alone. That fixes KT2 also is what? PM, metal vapor by activity of M. Since this is introduced, actually I mean, okay, I'm giving all, including all terms. Activity of M, equilibrium. Activity is what? M solid, pure solid. This leads to PM. So since this is known, so PM is also known. So what is the total pressure? Total pressure P. When I write P means total pressure, I write here P is the total pressure. Remember, you are already used to this. We have already defined this. Okay, so I have already said this total pressure. Not partial pressure, total pressure. Just mention P is the total pressure. Total pressure P. No confusion. So P, the total pressure is what? It is sum total of the partial pressures. What is this? PO2. This time 2 gases are there. So they together makes the total. This is known, this is known. That means, so temperature you have chosen yourself, means known, means defined. Pressure means, okay, known, pressure is known. And then composition. Composition, tell me, composition again, right? Composition of each phase. Composition again, like last time, right? M solid pure, what is the consequence? XM mole fraction is 1. So easy. Metal oxide solid pure. Composition means mole fraction is 1. And gas phase. What is the PO2? What is the XO2? Mole fraction of this. XO2 is what? Mole fraction is nothing but partial pressure of oxygen over total pressure. Is known. X argon, so I am very sorry. XM metal vapor. What is the mole fraction? Is PM by P, total pressure. So all you know. So this is so you can write this statement that thus the system is right. Thus, right here, from here. Here. Okay. This part is over already. Yeah. This is, I will remove this. I am starting from here. From here, thus, right, the last line, for satisfaction, thus, for convincing yourself, okay, for satisfying yourself, thus the system is fully defined in terms of temperature, pressure, and composition of each phase at equilibrium. This is the purpose of the phase rule. Okay, you can write here. This in case you are interested. I am writing here, but I will not write when pure you understand. This mole fraction is 1, xm is 1, and what you write here, xmo likewise, xmo is also 1 mole fraction, pure. So single species mole fraction. So this corollary to corollary 3 you will take up. So remove this. Here you take up corollary 3. So I am complicating this. The same. We are still in the problem 1. Corollaries to problem 1. What is the problem 1? Metal plus oxygen is this one. This reaction. This is the main. We are complicating. We are adding features. What feature we added here in this case? What feature we added here? Metal vapor. Introduce metal vapor also. Complicated. See, complicate. But no problem. Yes, degree of freedom is actually, anyway, we have discussed this. So it is good idea that so we'll take up now corollary last. Then only we will be able to complete first of the 12 problems. That will be used for the purpose of explaining the Gibbs Phase Rule and applying the Gibbs Phase Rule. So start corollary 3. This time what we are doing, I am telling you in nutshell, what we will do, this time again we will go back to metal solid, this only. No metal vapor, okay, introduction. No metal, no consideration. Metal, no, go back to simple, but we are adding another feature, a new feature. Instead of metal vapor, we are actually complicating that we are considering argon is present in the system. So metal oxide, oxygen, in addition argon gas is present. In presence of argon, a dilution. So we may add this. How it will change this? Okay, phase rule consequences. Okay, say degrees of freedom, on degrees of freedom, number of components, number of phases. See, on components, on phases, and on degrees of freedom. Consequently, so this corollary 3, let us write this out. Consider the chemical equilibrium chemical equilibrium 1. 1 means you understand? Here you have 1. Metal plus half O2 is MO. Metal plus half O2 is MO. So in presence of argon gas. in presence of argon. And make a phase rule analysis again. And make a phase rule analysis of the system. Figure, this is 1C, figure 1D. 1D is what we draw this. You can say metal solid, okay, right? Metal solid, metal oxide solid, again pressure, temperature T, and what are present? Oxygen, argon, and gas phase. Okay, and what else? Equilibrium. Figure 1D. That's it. So, okay, make a phase rule analysis of the system. Look at this. So again, like last time, start. Right? F is C minus P plus 2. We write this. Okay. Again, find C, find P, and substitute. C is what? Again, two different ways you try to always get this. C is what? Number of species minus number of reaction equilibrium. In short, okay, I am not writing independent reaction equilibrium. So reaction equilibrium. How many species? You tell me. See here, 1, 2, 3, 4 species. 4 species, 4. Minus number of reaction equilibrium. Only one here. Argon does not participate in the reaction. Inert gas. So only one reaction. 1. 4 minus 1 is 3. Right here, what are the species? Species are what? You write. Species is 4 is why? Metal solid, metal oxide solid, argon, oxygen gas, argon gas. 4 species. 4 species. Okay, 3. So number of element wise, let us say number of elements. This is cross check also. You may say cross check. You write this cross check. For the purpose of cross checking, these are number of elements. What? How many? 3. Again 3. Who are there? Metal, M, element, O, and new entry, argon. So C is okay. P, number of phases. You see clearly 2 solids and 1 gas. 3, 2 solids, 1 gas. Oxygen, argon make 1 gas phase. Okay, so 3. Go up here. C is what? 3. C is what? 3 minus 3 plus 2 is 2. Not 1. 2. This is the first time we come across 2 degrees of freedom. So what are they? Don't worry. You choose temperature, you choose pressure. Temperature say 700 Kelvin, pressure say 3 atmosphere. Just arbitrarily, independently, freedom, freely. Okay, you fix or specify. Okay, this. Okay, this okay. This is a TP. So you see fixing T leads to. Fixing T leads to. This better I write. fixing T leads to what? KT. KT of which reaction? Level 1. Only one reaction here. This time only one reaction. So no vapor. Metal vapor I have not considered. You may consider. No problem. Why? A metal oxide vapor also you consider. No problem. So, but I am complicating it already. Okay, so no harm. Okay, I am not avoiding anything. Okay. So KT1 is what? This fixes KT1 is what you tell me. As you know, 1 by PO2. You recall this 1 by PO2 equilibrium. So this gives you what? This gives you. Acha, this I have already know. This gives you. Acha, you make a fencing here. This gives you what? PO2 equilibrium. PO2 is known because KT is known. PO2 is known, and again fixing pressure. Fixing P is what? What does it mean? P is what? P contains what? Two gases, two gaseous species. So who are they? P oxygen, partial pressure of oxygen and partial pressure of argon, of which P is known because you have fixed P yourself. So you are allowed 2 degrees of freedom. You have 2 degrees of freedom at your disposal. Temperature utilize this way. Pressure knowing. Pressure is this. It must be sum of PO2 plus PO2 and PR. Okay. Total of PO2 and PR. So this is PO2 is known a moment ago. That means what it leads to? P argon is known. That means what? This one partial pressures are known, total pressure known. What is known? XO2 is PO2 over P is known. Composition. Now composition I am taking. X argon. X argon is actually, I tell you what. X argon is 1 minus XO2. The mole fraction always sum to 1. 1 minus XO2. In the gas phase, in the. Oh, sorry. Oh, no, it's okay. XO2 is okay. Is what it is? Similarly, P argon over total pressure. Yes, P argon over total pressure is also known. So composition, temperature, pressure, composition. Temperature, temperature, pressure, composition of each phase. Solid pure, two solids pure, and the gas phase composition is here. So this is, will you write that? Thus the system is right once more. That's right here. Thus here, maybe you write here. Thus, like this line you may repeat this. Thus the system is fully defined. Write this, is fully defined in terms of temperature, pressure and composition of each phase at equilibrium. But one warning is here. Warning. See, you have 2 degrees of freedom. Don't ever, I tell you, I give you the point. Okay, the argument is this: never fix T and PO2. Never consider T and PO2 as 2 degrees of freedom. TP, okay. TPO2. Why? Because T and PO2 are mutually dependent. See, T gives you PO2, so they are mutually dependent. But this should be independent. Degree of freedom is the number of independent variables that are required to describe the state of the system at equilibrium. Okay. So warning is what? So don't fix. Very important. See, another feature you are learning. This is another feature you are learning here. Presence of argon and also warning coming along with it. And a moment ago, inclusion of metal vapor. See, so you see, so remember these things. Okay, also understand this and appreciate this, and then use this yourself. Okay, don't fix F is 2 as T and PO2. T and PO2. These choices are wrong. Why? Are wrong as T and because T and PO2 are mutually dependent. Dependent variables. So careful about this. Warning, box this. Warning, very important for you. So this is okay. This you can see here. You fix in temperature, PO2 is automatically fixed. And also you see, you will be trapped. You will be trapped. You will be cheated. See, you will lose. See what? Suppose you by mistake you fix T and PO2. Say T. Where is this? T PO2, not P PO2. See, let it be so. Then what you are doing? You apply. Then why not going to T PO2? How will you choose freely? T PO2 is dependently fixed. So yeah, what will you do? Then you cannot move to T. First of all, it is clashing with what you have chosen. T fixes PO2, but what you have chosen is different. So clashing. If you choose this one, then that is not choice. This is already chosen for you. That is not choice. Your choice can vary. Should be flexible. Here T wants fixed 700 Kelvin and PO2 say 0.3. So 0.3 it cannot be otherwise. So you cannot say 0.4. So this is no. So you cannot choose anymore. Once fixing here fixed T means PO2 cannot will be dependently fixed at that value and rigid there. If you say that is ridiculous. If you say I am choosing this temperature and PO2 this, see you cannot actually be insensible. Impossible thing, okay? PO2 it is like contradictory. So what is happening? So don't. So that moreover, suppose then what is the total? Suppose you continue to argue. Then tell me what is the total pressure? What is the argon pressure? What will you answer? No answer. Yeah, your weapons are all exhausted in the form of T and PO2. Wrong choice though. Utterly wrong choice or totally wrong choice. Wrong combination. How will you get the pressure of the system? Argon pressure, partial pressure of argon. No answer. Looks good?
Okay.
How much time left? Okay,
30 minutes left. 1 hour 30 minutes.
so 30 minutes is okay. Come back. 30 minutes. Come in the middle also once more, if possible. So this you have to consider. So okay, now what we will do? Example 2, second problem. Start. About these figures I have already drawn. So first problem is over. 1 of 12 over. This is next is what it will be. Example 2. So second problem. Second example. Start. What is this? What I say? Let me write. Like I wrote actually this one. In case of first problem, I am writing. This is also a chemical reaction. And very popular chemical reaction to the metallurgist, to the blast furnace people, is what? Ap solid plus CO2 gas. No problem. Okay, this is call it equation. Again, since it starts here, second problem, so I start with equation 1. Okay, no problem. So just wait a bit. Wait a bit. These are not required. These are not required. So remove this. Remove this. Okay, so let us move on now. Now it is now clear. So make the phase rule analysis as usual. See, F is right. Begin with this. F is, first of all, find the value of F. Then demonstrate how by fixing F number of variables the system is fully defined in terms of temperature, pressure and composition of each phase at equilibrium. Job, you know very well. 100 times you have heard from me. So C, first of all, C is what? What, you know, go ahead with number of species. Well, I should actually draw a figure, no? That will help you, you know. That will certainly help you. Again, pressure. This is the temperature T. And these, what are the phases present? Fe solid, FeO solid. And what gas? CO2 gas. Gas phase. See, FeO plus CO goes to Fe plus CO2. Okay, FeO solid plus CO gas goes to Fe solid plus CO2. Start. Number of species minus number of independent, I am not writing, reaction equilibrium. Equilibria. How many? Number of species quickly? 1, clearly 1, 2, 3, 4. Here also 1, 2, 3, 4. 4 species minus 1, only one reaction. Only one reaction is what? 3. And it's mentioned here species are what? Just in case of difficulty, species are 4 species, right? Fe, FeO, CO, CO2. 4 species. Okay, 3. And alternative definition of C is what? Cross check. For the purpose of cross checking, C is number of elements. Number of elements. Let us see. Is what? Is also 3. Who are there? Fe, C, O. Okay, very good. So 3. So it is now use this and P. Number of phases. P is the number of phases. Write this number of phases. What it is? How many? Two solids. Pure two solids. Two solids and one gas phase. So 3. 3 is what? Two solids. One gas phase. Gas phases always make one. Okay. All gases will form single phase. One gas phase. Use this. C minus C is how many? 3. P how many? 3 plus 2. So again 2 degrees of freedom. Again you consider temperature and total pressure. Very helpful. Okay. So temperature. So this is temperature, pressure. Okay. Fix this. As a fixing T. Fixes what? KT, equilibrium constant of 1. The reaction under study is what? What is this? This time write activity of Fe, PCO2, activity of FeO, PCO, equilibrium. And you know this is 1, that is 1. Solids, pure solids. So PCO2 over PCO under equilibrium. Just I am not writing this. Okay. And another thing, what you have chosen, fixing P leads to what? Leads to what? P is what? Oh, sorry. P. This P. Okay. P is what? Remember, the lowercase p and uppercase P is the number of phases. Make no mistake. Don't confuse. P is the total pressure. Fixing P gives you P is what? Tell me what are the gases? Partial pressures of the constituents PCO plus PCO2. Call it equation 1, 2. 1 is already there. 2. This is 3. So 2 unknown. PCO and PCO2, 2 unknown. 2 equations. Solve equations 2 and 3 for what? PCO and PCO2. So PCO is known, PCO2 is known. This gives you what? PCO, PCO2 is known means XCO. This leads to XCO. You know, XCO is PCO by total pressure. So no difficulty. And XCO2 is 1 minus XCO or PCO2 by total pressure. This is known because everything is known. PCO by P. PCO is found here and P already you have chosen yourself. So composition, temperature, pressure, composition, you may write that or you may not write. So by fixing, so write. So and gas phase and other solids are pure here, so it's the same thing. Okay, so you write this. Okay. Alright, you can add here Fe solid pure means composition is mole fraction is 1. FeO solid pure means is what is the composition of FeO solid is single species, so 1. Okay, these are pure. So by fixing the F using the F is F variables, F which is 2, F is 2 variables 8 variables means 2 variables. The state of the system is fully defined as you write the system. Actually, this system is fully defined. I am writing saying the state of the system. Better implied state of the system. The system is fully defined as state of the system. So you add this the state of the system is fully defined, or you may write described in terms of, as you write, temperature, pressure and composition of each phase. Which phase? At equilibrium. Oh, here also write equilibrium. Sorry, I forgot to write this. This is equilibrium situation, and what it has been said here? Oh, I have not mentioned this. This is this should be figure 2A. Figure 2A. This is 2B. 2B is coming. Figure 2A. This is the original setup. Okay. Description of the system. 2A. A sketch of the system. 2A. This will be 2B coming to this. So figure 2A, and this is also right. Equilibrium always is under equilibrium. Okay. So this part is over. Initial part is over. So now stability diagram constructions. Okay. This is very important. Now I will actually go up there. So I will actually give this is a stability diagram for the system FECO. This is the stability diagram. This I will show you actually. This is a plot of PCO versus PCO2. This I will show you. So for this, so continue this and you remove this upper part. This is actually first problem discussion. So remove this. Don't worry, remove altogether. So I will actually consider this next. Yes, now it is now good set. I may write now. Let us use this because this will be construction of stability diagram. So good idea that I actually start fresh from here. So what is to be right? Yes, it is better actually. So this is this part is okay over. So stability diagram may write. Problem 2 continue. Give a star here. Star there. Stability diagram. Stability diagram. Okay. You follow with me. You follow this. Here from 2. From equation 2, PCO is 1 by KT1 equilibrium constant pure. Okay, is what times PCO2. So PCO versus PCO2 plot is linear. Okay, So PCO versus PCO2. So PCO versus PCO2 plot will be what? What? This is a constant. 1 by T is a constant. As we fix the temperature, it is a constant. Like say 4.3, 0.05, etc. So plot is linear, means straight line. Which one? Now see, come down here. This is figure 2b, right? Figure 2b. No problem. Okay. This is linear. This is shown in the figure 2b. Which line? There are too many lines. Don't worry. PCO versus PCO2. See figure 2b, stability diagram for the system APCO. The three components is a APCO, so that's why APCO system we say. This line, please consider this line only. Acha, what is the slope? Positive or negative? See, equilibrium constant can never be negative. Can never be negative. It can be zero when equilibrium constant will be zero, when delta G0 is plus infinity. Delta G0 from where I am saying this? Delta G0 is minus RT ln K. If delta G0 is plus infinity, then equilibrium constant is the least possible value. What is that value? Plus infinity means ln 0 is minus infinity, minus plus infinity. So equilibrium constant is 0. Negative, impossible. Positive. Then what it can be? Then it can be decimal, 0.1, 0.01, 0.001, 0.01, 0.11, 2, etc., etc. 10 to the power 2, etc., etc. It goes. Okay? High and high. Okay? Large values. Okay? All large. It can go up to infinity. Okay? So 0 to infinity is the domain of for K values. Don't worry. Negative never. So it is 1 by K. This is also positive. Kt is positive. So what is the slope? Positive slope. You clearly see this line. Positive slope. See this. How do now? Let me explain. This one. Okay. Once drawn. Very good. Very good. Okay. I'm sketching this. I'm kind of sketching these equations, etc. This discussion here in this graph. Stability diagram very useful and linked up with the phase rule. Very easy to follow with the help of phase rule. So this is the equation. Yeah, this one. This I plotted. Linear. This. Not this. These are different. Different things. What they are? So this line again. First complete. So this line you follow with me. Positive slope. What I have written anything here? Here which are, see along this line which phases are present? Tell me. Along this line, APO, CO, CO2 gas. CO2 gas. So along this line, APO, first of all we consider. Then you know these gases are showing on the y-axis and axis. Refer to the axis also. See which gases. So this is implied. So APO, CO2 gases, CO2 two gases, one gas phase, phase-wise one gas phase, are present along the line. So most important, CO2 is implied as the y-axis and x-axis suggest. So along this line, two condensed phases, two solid phases are present. Pure, APO. So above the line, below the line. Always above the line, below the line, or to the right, to the left. Anyhow we consider. So follow this line. Don't ignore these two lines for the time being. I'll come back. That is about total pressure. Superimposed. Don't worry. Only this line. So above this line means what? CO is increased as if keeping CO2 fixed, CO is increased. CO is increased, then what will happen? If CO is increased, reaction will move this direction and moves sustained. You have sustained this, so moves. APO is diminished, finally eliminated from the system. What will be stable phase? AP solid. See, as CO increases, AP solid alone means solid wise alone, and of course the gas phase, the CO2 plus CO2 gas phase. This is, and below this line, mean what happens when CO is decreasing, CO is below the equilibrium value, then the reaction will move to the left hand side and AP will be eliminated. Now what will be the resulting phase? APO solid plus APO solid and plus of course the gas phase, CO2 mixture. So along the line AP, APO both, and above the line AP alone, AP solid alone, and below APO solid alone. Okay, and and gas phase accompany them always. So what this is okay. Now what I have done here, additional thing I have done. This diagram is over there. It's over. But I have shown you these situations that where actually I have fixed some pressure and temperature. This actually I wanted to show with the help of the diagram. So this is, you consider this. Shall I write here? I'm plotting what I have plotted here. So this line is okay.
1 hour 51 minutes gone. 52 minutes.
Okay, 8 minutes. Okay, very good. So this will be actually okay. So very good. So now you see. So P, another plot coming. Okay, that is. P is, say, P is fixed. Any P fixed? Temperature, pressure, P is fixed at 1 atmosphere. Say, that means what? Is what? PCO plus PCO2. So if you want to, what is the equation you generating? Or PCO in terms of these two coordinates, PCO and PCO2 relationship you generate. Or PCO is what? 1 minus PCO2. This is the equation of the total pressure when the total pressure is 1. Okay. So PCO is 1 minus 1. So what does it mean? PCO versus PCO2 plot is linear. Against straight line is linear. Good idea that I actually linear with a negative slope, with positive or negative slope, minus PCO2, negative slope, with a negative slope. Negative slope. Negative slope. Achha, negative slope. What I am doing, superimpose. Original line is there already, FFO line. This equation 1 is drawn. This equation is drawn. That is the stability. This is the, why stability? Why the name stability? That is another thing. AP solid is stable in this domain. Quickly. AP solid is stable in this domain. Here, above the line, domain. APO solid in that domain, below domain. Okay? And along the line, APO. Okay? See, what happens? This, you see? So this is, okay, very good. This is, okay. So along this line, APO both. And of course, gas phase accompanies them. Okay. So for example, here along the line APO and gas phase, CO2 mixture, and above the line AP solid and the gas phase, CO2 mixture, and below the line APO solid and CO2 mixture. So we often write the condensed phase only. Gas phases are understandable from the y-axis and x-axis. Take a look at the y-axis, then you understand. But now I am superimposing this line. Which line? See, follow this line. The first one, this one, negative slope. This line. What I have said, this is actually P is PCO plus PCO2 is 1 atmosphere curve. So this curve, this is P is PCO plus PCO2 is 1 atmosphere. Total pressure is 1 atmosphere curve. Very clear? What means PCO plus PCO2 constant at 1 means see the nature of the curve. As PCO2, when you come down, PCO2 increases, PCO comes down, decreases. So go down this way CO2 increasing and CO decreasing. Okay, or the reverse way, CO increasing and CO2 decreasing. So makes sense. The total is 1. So what is the value? 1. Another line I have drawn that is exactly same. Instead of 1, I have considered 2 atmospheres. So I have drawn it parallel. It should be 2 here. So it should be parallel line. Parallel I have drawn here. So I have written here it is 2 atmosphere curve. Okay. Then they intersect at this point. What is the one by one? So consider the first one. P is 1 atmosphere line and the FPO line. They intersect at this. What is the significance of this? The significance of this here, which are present, FPO, the equilibrium coexistence. I have written here. Equilibrium coexistence of FPO, CO2 at 1 atmosphere. Okay, the pressure that you have chosen, this point signifies that the equilibrium coexistence of FPO along the line means FPO and the gas phase. In any case, outside this intersection point, there are FPO, CO2 along the line. As long as it is on the line, FPO, CO2. What is the special about this point? This point is that at 1 atmosphere, because it has intersected this has intersected the 1 atmosphere line. So this is at 1 atmosphere. Similarly, this has intersected this line, which is 2 atmosphere line. So this is the similar thing. Equilibrium coexistence, I have given ditto equilibrium coexistence of FPO, CO2 at 2 atmosphere. This is the significance. So if I have write, I write, or I don't write. Is okay? Very good. So figure 2b, I have written here, figure 2b is okay. So slope, negative slope, what I wanted to write here, this you write it, that is, it is superimpose this line. This line is 1 atmosphere or 2 atmosphere line is superimposed on the FPO stability line. So superimpose this line means this, okay, 1 atmosphere or 1 atmosphere I have considered, this 1 atmosphere line, this line on the FPO line, FPO line, on the FPO line, okay, means this curve, FPO, okay, this line, where FPO coexist. So what is this referred to? Figure 2b, okay, 2b, right. This part is okay. This part is very good. This part is very good, and very good. Okay. So now figure 2b. Okay. So this part is over. So next is actually alternative stability diagram. Write this. Alternative stability diagram. That I will draw. Okay. Figure 2c that will be. That is. But what is the principle behind this? Follow this. KT is what? You follow. I don't want to disturb this part. You know, this part is very. I don't want to. Okay. But this is actually, since problem 2 is still running. Okay, so don't disturb. This is the main reaction. This is the understudy. This is the system. This is the reaction system. This under equilibrium. Applying the phase rule. Drawing the stability diagram. These are the jobs on hand. So alternative stability diagram, okay, of the system. FPCO. This how much?
2 hours gone. 2 hours 39 seconds.
Okay, stop this. So I think it will take some time. So it is better I actually take up this next class. But today actually thank you very much for your okay all attention and for your interest and for your cooperation. Thank you very much. So we see you. We see you actually. I will meet again next class and okay, and I wish you actually very warmly and very cordially very happy New Year 2026. Thank you. See you next class. Bye.